All right, in this first section, we are going to discuss titration and what it is. Titration is used to determine the concentration of an unknown solution. It is an experimental process of adding a known quantity of one solution, known as a titrant, to a measured sample, known as an analyte, to react in a definite known proportion. The concentration of one of the solutions is known, and that is called the standardized solution. The standardized solution can be either the analyte or the titrant. The addition of the titrant is stopped when the equivalence point or end point is reached. For all titrations, we determine the end point by a color change when the analyte reactant is fully consumed. So we're going to measure, we'll see as we do our titrations, the color change happen. And as soon as that happens, we know we've reached our end point. For an acid-base reaction, the color change is detected with the help of an indicator that we will add to the analyte. For a redox reaction, the color change is due to the reaction itself, so an indicator is not used. So in the figure, we have the basic setup of a titration. The fixed volume of the analyte is measured using a pipette in the flask. So we have a fixed volume of our analyte in this flask that we've measured. The titrant is slowly added from this instrument called a burette. When the solution in the flask changes color, then we stop the addition of titrant. Then we can measure from the burette the volume of the titrant used. This technique is also known as volumetric analysis because both reactants are in solution phases and the volume is measured from the burette. Reading the burette. There are some things we have to keep in mind when we're reading the volume from the burette. It's important to accurately read the starting and ending amounts of liquid in the burette when doing a titration. The surface tension of a liquid causes the liquid in a container, including a burette, to curve up or down. This is called a meniscus. So curving up is convex, curving down is concave. It's important that you read from the center of the meniscus, either the top of the upward bulge right here, or the bottom of the downward bulge right here, indicated by this red arrow. Some liquids, such as water in a plastic container, don't form a meniscus and are therefore easier to read. Acid-base titration. In acid-base titration, a fixed volume of the analyte is measured using a pipette and transferred to a beaker, or in this case, an Erlenmeyer flask. This would be our analyte here. And we know the volume of that. We know the milliliters or liters of that. In this case, in the case of an acid-base titration, a standardized acid or base solution, the titrant, so the titrant would be in the burette, and it would be a standardized acid or base solution, would be slowly added to the analyte, which is either base or acid, of unknown concentration. So we don't know the concentration of the analyte, but we know the concentration of the solution in the burette. The titrant is dispensed from a burette to the analyte in an Erlenmeyer flask or beaker. By measuring the moles of titrant added, the moles of the analyte can be determined, and therefore the concentration. Indicators are used to determine when a solution has reached the equivalence point or end point during a titration. The color of the solution changes when the equivalence point is reached. The equivalence point is the point at which the stoichiometric amount of acid equals that of the base as per the balanced equation. What that means is that at the equivalence point, the moles of acid equal the moles of base. Mathematically, the concentration of the acid times the volume of the acid, that would give us moles. Remember that concentration is moles per liter. And if we multiply that by liters, we're left with moles. So this results in units of moles. For the acid is equal to the moles of the base, or the concentration multiplied by the volume. The solution changes color rapidly at the equivalence point. This point is also known as the end point and is the time that you will stop adding the titrant. The end point is the appearance of the first permanent color change of the indicator. This point will have a slight excess of the titrant in the solution. Acid-base indicators are mostly made of complex organic acids or bases. Their dissociation step resembles that of a weak acid or base. The dissociated and undissociated forms have different colors. As the medium changes from acidic to basic or vice versa during a titration, the equilibrium shifts, so the color changes. With strong acids or bases, a commonly used indicator is phenolphthalein, which we will symbol with HPH here. So phenolphthalein, HPH, in water is colorless. But this equilibrium exists where this phenolphthalein, HPH, can dissociate. All right, and so then we have the hydrogen ion and this conjugate base here. This hydrogen ion is colorless, and this ion is pink in color. So phenolphthalein is pink when the pH is 8.2 or higher. Here's how indicators work. In this reaction, HIN represents a generic acid-base indicator, which is an organic weak acid that changes color when an acid or base is added to it. So here's our generic indicator, HIN, which is yellow in color. IN minus represents the conjugate base of HIN. If H plus acid is added to the indicator, the reaction would shift to the left in accordance with Le Chatelier's principle. So if we add acid, that would be adding this, and then we would shift to the left, right? The reaction in that case would be yellow in color, since the reactants are yellow in color. If base is added, hydroxide, base is added, the reaction would shift to the right, making more products, and therefore the reaction vessel would look blue. Depending on the pH of the solution, the indicator changes color between yellow, in this example, and blue. Several acid-base indicators are available to use for titrations involving various acids and bases. The selection of the indicator is determined by the type of acid and base used and the pH at the end point. So if we're expecting an end point that's very low, from this 0 to 2-ish range, we would pick methyl violet or thymol blue. As we increase where we would expect our end point, we might need to pick a different indicator, methyl orange, methyl red, bromethymol blue. Indicator changes color around a pH of 7. Phenolphthalein is from, you see, 8 to 10, so around 9 here. Thymol blue has another endpoint there as well. And then alizarin yellow has the highest endpoint around a pH of 11. A pH meter is used to measure solution pH during titration. Various digital models and simple probe types are available for use. The pH is measured at the beginning before any of the titrant is added. pH is then measured after each time when a small amount of the titrant is added. The variation in pH depends on the type of acid and base used in the titration. And we'll talk about the various combinations of types of acids and bases in different titration examples as we go. But the pH will change suddenly very close to the end point. The pH is recorded beyond the end by adding 2 to 3 milliliters more of the titrant, and at that point you should again see the pH level off. In practice, titrations require 2 trials and often 3. The first trial finds the approximate location of the endpoint using large amounts of titrants. The second, like 1 milliliter at a time. The second trial slowly adds smaller amounts of titrant before the estimated endpoint, so add in smaller increments, 0.05 milliliters. The third trial may be needed to confirm the results of the second trial. The addition of the titrant in the final trial should be as small as possible toward the equivalence point to get accurate pH measurements. The pH value versus the volume of the titrant is plotted to determine the volume of the titrant needed to react with the analyte. The plot that you see on the right is known as the pH curve of the titration. And we're going to discuss it in a lot of detail later. But here's what we have to know. What we're measuring here is the volume of 0.100 molar NaOH, this is our titrant, being added to our analyte, and we're measuring the pH. So as the volume increases, we see the pH going up, and then it suddenly jumps very quickly, okay? And we can determine the endpoint or the equivalence point from this graph. It's the point halfway between this big jump. And in this case, it's at pH 7. And then as I mentioned in the last slide, we're going to continue to add for a few more milliliters to make sure that we have fully reached that endpoint as the pH continues to increase. All right, here are the steps to prepare for an acid-base titration. First, rinse the burette with distilled water. Then, coat the inside of the burette with titrant by adding 2 to 3 milliliters of titrant, and then you turn it horizontally. So we're going to just rotate it horizontally and then spin it around, rotate it to get the inside of it coated, and then empty the titrant of all of the liquid. Once we've coated the inside with titrant, the next step is to fill the burette with 50 milliliters of titrant and drain a small portion here. We're going to open the stopcock so that we can drain a small portion so that there's no air bubbles near the tip of the burette and it's fully filled to the tip. Then, whatever pipette we're using to transfer the analyte to the flask, we also want to rinse the pipette according to steps 1 and 2, first with distilled water and then with some analyte, and then transfer a fixed volume of the analyte from the pipette to the flask. Add 1 or 2 drops of indicator to the analyte flask, and then you're ready to begin your titration. The amount of titrant used is found by subtracting the initial reading from the burette from the final reading of the burette at the end point. One thing to keep in mind is that burettes read from top to bottom. So 0 milliliters is at the top and 50 milliliters is at the bottom. So if we start with the burette completely filled with 50 milliliters, then we're starting at 0. And then we should see the titrant move down a measurable amount. The initial reading is 0 if we fill it to the top, and the amount of titrant used then would just be equal to the final reading. If it's filled to a lower level, such as 5 milliliters, that value then has to be subtracted from the final reading. Let's talk now about the equivalence point of a titration. The net ionic equation for any neutralization reaction is aqueous hydrogen ion and aqueous hydroxide ion combining to form liquid water. For every hydrogen ion, there must be one hydroxide to react. A monoprotic acid, like the generic acid HA, will donate 1 mole of hydrogen ions for every mole of acid. Diprotic acids, like H2A, will donate 2 moles of hydrogen ions for every mole of acid, right? So this would be 2H plus A minus, right? Now, monobasic bases. So a monobasic base would be something that has a metal ion and a single hydroxide. They can accept 1 mole of hydrogen ions for every mole of base. And why is that? Because we have the metal ion and 1 hydroxide, so we can accept 1 mole of hydrogen ion in the formation of water. But what about a dibasic base? So that would be some metal hydroxide that would have 2 hydroxides. And so we would need 2 moles of hydrogen ions accepted in order to neutralize these 2 hydroxide ions. Here are some examples of reactions in which the ratio of moles of acid to moles of base is 1:1. A monoprotic acid like HCl, HBr, HNO3, or acetic acid, CH3COOH. We have this 1 acidic proton. Reacting with a monobasic base. So see, in every case, these metal hydroxides have a single hydroxide. Okay, and that results in the production of a single water. So the molarity or volume of acid or base at the equivalence point would just be molarity of acid, volume of acid equal to the molarity of base, volume of base, because the ratio of the moles of acid to moles of base is 1:1. Here are some examples of reactions in which the ratio of moles of acid to moles of base is 2:1. A monoprotic acid reacting with a dibasic base. So the acids, if you see, there's 1 proton to donate, but the bases have 2 hydroxides. And so in order to balance this, we have to have 2 moles of the acid and 2 waters are produced. Now, how does this set up our ratio here? Our moles of acid has a coefficient of 2, and our moles of base has a coefficient of 1. So our ratio of moles of acid to base is 2:1. Remember that moles of acid is the concentration times the volume, and the moles of base is the concentration of the base times the volume of the base. If I take this and I rearrange it by moving this molarity of base times volume of base, I get moles of acid, molarity of acid times volume of acid is equal to twice the molarity of the base times the volume of the base. Okay. Here are some examples in which the ratio of acid to base moles is 1:2. So we have a diprotic acid reacting with a monoprotic base. And what do we have to do to balance that? We have to double the moles of the base. Double the moles of the base. So moles of base is twice the moles of acid. So moles of acid, molarity times volume, over moles of base, molarity times volume of base, is 1 to 2. Again, just rearrange. I multiplied the 2. So 2 times the moles of acid, molarity of acid, volume of acid, is equal to, multiply this over here, molarity of base times volume of base. Okay. And what this is saying is the moles of acid equals the moles of base. What we're saying is the moles of base is equal to 2 times the moles of acid. And the stoichiometry tells us that. The moles of the base is twice the moles of the acid. Titration equations for equivalence point. The 3 combinations of acids and bases and their titration equations are shown in the table along with examples. So if we have monoprotic acid and base, it's straightforward. MAVA equals MBVB. If we have a diprotic acid and a monobasic base, it's right here in the name. The acid is diprotic, so the number of moles would be twice the base. So 2 MAVA equals MBVB. If we have a monoprotic acid and a dibasic base, again, the moles of the base should be twice the moles of the acid. So MAVA is equal to 2 MBVB. 50 milliliters of sulfuric acid is titrated. That means it's the analyte. So the analyte is 50 milliliters of H2SO4. Is titrated with, so our titrant, 0.100 molar sodium hydroxide, 55.50 milliliters of the base is used to reach the end point. What is the concentration of the acid? Okay, so I've summarized here. And then we're going to look at how to solve this on the next slide. All right, the acid is the analyte, as we said, and is pipetted into the flask, and the base is dispensed from the burette. So this is our titrant. The amount of acid is exact and fixed. The amount of base depends on how much is required to reach the endpoint, and we're told that that's 55.50 milliliters. Now, this is a diprotic acid, H2SO4, and a monobasic base, okay, because we have one OH. So our equation is 2 MAVA equals MBVB, where capital M is the molarity. What are we looking for? We're looking for the concentration of the acid, which is MA. So I rearranged the equation to solve for the concentration of the acid and then substituted the values. The known concentration of the base is 0.100 molar. The known volume of the base, 55.50 milliliters, divided by 2 times the volume of the acid, 50 milliliters. After calculating, we get that the concentration of the acid is 0.0555 moles per liter.